Welcome back, my fine young Drosophila melangoster, to Frictional Forces. Friction, it's a drag. We're going to look at the few last things here. What is the normal force? What is a frictional force? A friction coefficient, and we'll look at human joints, jet altitudes, hyperloop, and the societal cost of friction. You're going to be able to explain what the normal force is, connect the normal force to Newton's third law, and calculate the value of frictional forces resulting from the normal force and an object against a surface. And you will distinguish between the coefficient of static and kinetic friction. And it's all something you've experienced in life, so it's actually really quite easy. I've got a series of videos I'll post that I want you to watch that deal with friction, and I'll probably add a few more, and we'll do some societal cost analysis of friction here, because most people never think that something as lowly as just oil, any lubricant, is as important as it really is. The third law, remember, states that all forces have an equal and opposite reaction force. This comes from the other body. So if you push on a wall, it pushes back on you. Recoil of a gun is a classic third law situation. Gravity is a force field. What this means in practice is you do not have to touch an object to feel its gravity. You do not have to touch a magnet to feel the magnetism. But friction is a contact force. You must physically touch the other object to experience friction. So this mass will accelerate towards the Earth whether or not it touches the Earth. The normal force is a contact force. If a solid surface is between the Earth and your feet, that solid surface is preventing the object from accelerating. An equal and opposite force is created by contact. So your mass downwards is not the force. Your mass times gravity is the force, and the surface will push back with the exact same force. If it did not, you would start accelerating towards the center of the Earth. Does every surface provide a normal force? No, absolutely not. If you go walking out on soap bubbles, you are far too massive that your gravitational force will exceed what that surface can hold, and you will plunge through it. If you decide to go walking across grass, it will probably provide the normal force. But if you decide to go walking across wet grass wearing stiletto heels, the surface won't be able to support that, and you'll punch through it. Now, normal means 90 degrees in math, and unfortunately, mathematicians could never make up their mind what perpendicular was called. So they will call it normal, orthogonal, right angle, perpendicular. These are all terms meaning 90 degrees to a surface. The surface pushes back on the object with as much force as it received. Equal and opposite cancel out, and the object cannot fall unless the surface is not strong enough to provide this normal force, and deformation or collapse takes place. So the normal force is equal and opposite to the force of gravity, a Newton's third law situation. And it seems like we're making too much of a big deal over nothing, but this is really important. It is an entirely different force. It's atomic in nature, and it opposes gravity, but it's from a very different source altogether. Friction is another contact force. When an object is pressed firmly to the surface, there is an attempt to move it, then a friction force will appear fighting the motion. It doesn't have to be accelerated motion that it fights. So a force of friction will appear even if you're at constant speed. You know that. If you stick your hand out the window while Dad's got the car on cruise control, the wind friction keeps on going even though you're not accelerating. So there'll always be a force of friction opposing movement. Now we can use that word instead of insisting it be acceleration. This force will always oppose motion. It can never help motion, and it depends on only two things: the force of gravity or weight and the roughness of the two surfaces on contact. This roughness is an index. You did index of refraction in grade 10. This is the coefficient of friction, and its symbol is the Greek letter mu. There are two versions of friction, mu kinetic and mu static. What does that mean? Whenever you've slid something, let's say you're trying to push a fridge, it fights, and then you feel like click, and it unsticks from the surface and begins to glide. If you let something sit still for even a brief moment, it actually partially welds itself down to the surface through atomic bonding, and you will find if you're trying to slide something, get it moving, you find there's a very heavy force at first, and the second you get it moving, it gets slightly easier to keep it sliding. How do we calculate the force of friction? People with no social life spent centuries sliding objects on other objects. Going, yeah, I'm going to rub pine against oak. Cool. Now I'm going to rub pine against fir. What kind of fir? The tree or a cat? Both. Then I'm going to rub pine against wax. And they just started measuring the relative friction. So basically what we say is the friction is this multiplier times the normal force. But then you go, but didn't you say the normal force is the same as gravity? Most of the time it is, but you'll see why we need to roll it differently. So we have our normal force, and we want to interpret this mu. The normal force is really the force of gravity in terms of size, but the force of gravity is another name for weight. Fg is the force you would need to lift it. A 100-pound weight needs a 100-pound force to lift. In metric, a 50-kilogram mass needs 50 times 9.8, m times g, approximately 500 newtons to lift. This is the drag you feel if you try to slide it. A 100 Newton drag would feel the equivalent to a 10 kilogram weight being lifted. Remember, you can take any force, knock off 10, just divide it by 10, and that would give you the equivalent weight. So you can think of the frictional force as the fraction of the weight necessary to push it. So let's say, for example, there's a 500 Newton weight. A 50 kilogram object sitting on the ground weighs 500 newtons. And the coefficient of friction is 0.2. When you multiply these two numbers, you would get 100 newtons of drag, which is 1/5 the weight of the object. So the example here, it would be 5 times harder to lift it than to slide it along the floor. And that's how I'm going to get you to try to interpret this so it makes sense to you. The coefficient, by definition, coefficients have no units. It's a multiplier that is basically telling you what percentage of the object's weight will you feel as drag. So if the coefficient of friction is 0.9, you are going to have to shove with 90% of the force that would be required to lift that thing. If you are on ice, can you imagine what the coefficient of friction is? When you shove an object on ice, like a curling stone, what do you have to push? 1/100th of its weight? 1,000th of its weight? Let's say you go, I lifted that curling stone and it weighed 10 kilograms, but I pushed it, it was light as a feather, so I bet you it's only 0.001 of its weight is what it took me to slide it. Then you understand the coefficient of friction. Now, if mu reached 200, you might as well pick it up. Because if mu goes over 1, then it's harder to slide it than it is to lift it. And you've probably all been in situations where you discovered some objects, they are so hard to slide, you might as well just pick them up or put them on wheels because the drag is too high. Here would be an example. There's a 50 kilogram mass. So the downwards force is 500 newtons. That means its normal force is 500 newtons up. If I said this surface has a mu of 0.6, then 60% of its mass, or its weight, will appear as friction. So the force of friction is 300 newtons to the right. Because remember, this guy is pulling the mass towards him. So the friction goes the other way. Now, what would that feel like? That would be the equivalent of this guy hanging a 300 newton mass or 300 newton weight over the cliff. Well, 300 newtons would be the equivalent of 30 kilograms. So this 50 kilogram object, he's going to be pulling with 30 kilograms of force, which is 300 newtons of force, against it. So it would feel like someone's hung a 30 kilogram mass over the edge of the cliff in terms of interpreting this friction. So a frictional force of 300 newtons would essentially feel the same as a dead weight of 30 kilograms. If you calculate a 1500 newton frictional force, it would feel the equivalent as 150 kilograms dead weight. However, what can the mass do that friction cannot? My substitution of friction for a weight makes the force understandable, but this is by no means a proper substitution. That weight can do something that friction cannot do. If this guy here lets go of the rope, does the frictional force continue? No, it vanishes. Friction only appears when you try to move something. It's like the instant anti-karma. Every time you try to do something, friction shows up and fights you. But if we said, oh, this is the equivalent of friction, and this guy lets go of the rope, is that mass going to vanish? No. So this was just to give you a perception of what the size of that force is, but no way are these two situations equivalent in terms of real-world behavior. Let's have a closer look at the formula. Why the normal force and not the gravitational force? Aren't they the same? Yes, they would have the same value in newtons, but only on a flat surface. And the normal force is a contact force from a surface that was pushed on. And it was pushed on by gravity, but it could be pushed on by other things. There's still going to be friction in outer space. Let's suppose you tied a pulley system down really tight. You could create friction between the pulley and an object, but the object's not affected by gravity. It could be hooked up by a spring. So the Earth pulls down an object. There's a new surface in the way. The surface pushes back. But that downwards force of gravity does not have to be the initiating source of the normal force. You could have a magnet stuck down to a sheet of metal and you try to slide the magnet on. So the normal force is not created by gravity. Gravity just happens to be the initiating push against a surface in the problems we will do. But again, you take a square magnet, stick it on a metal plate on the space station, and there's a normal force. It just didn't originate from gravity. So that's why we're distinguishing between it now. In grade 12, this is what you'll do. You'll have force of gravity straight down. Then there's going to be a force parallel to the ramp and a force perpendicular to the ramp. And now the normal force will not be completely gravity. It will be a component of gravity. And you can see if this ramp tipped to the vertical, there would no longer be any push against the surface. Gravity would pull straight down and the normal force would vanish. Okay? That's what you get into in grade 12, and that's why you got to get used to using the normal force, not the force of gravity. They have the same value only on a flat surface and only in a situation where gravity is what's doing the pulling. And other than that, the normal force does not have to match gravity.